Et puis, le choix. Qu'est-ce que vous avez entendu parler?
Oui, bien sûr.
Je crois qu'on a mis bon, c'est possible. Après, j'étais pas très. Non, parce qu'il y a 2 ans. Ah oui. On est live sur YouTube. C'était un peu compliqué aussi à l'antenne. C'était les piles de 3 mois.
Oui, c'est ça. C'est très peu de personnes qui
C'est sûr.
entendent tout.
Après, il a trouvé plus que moi pour la suite. Sinon, je suis encore sans réponse. Ça va. Il manque Olivier en ligne. Ouais, ouais. Lorenzo qui a dû changer le. Il était dans la salle robot, mais il y a les gens de Paolo Robotics. Du coup, il a dû bouger l'ordi fixe dans une autre salle. Ouais, il est arrivé même quand j'étais là la semaine dernière, il y était dans des grosses boîtes. Salut.
Encore, c'est 9h30.
Ils sont à côté, ouais, c'est 9h30.
Le président.
Pardon?
Il désigne le président.
Probablement, ouais. Ceci dit, je crois qu'ils sont allés au café là. Oui, oui, bien sûr. Ils sont plus à côté. Ouais.
J'ai eu salut Chine.
Oui, je le rappelle aussi. C'est surtout ça qu'il faut que je règle. Après, bonjour Olivier.
Bonjour Maxime, est-ce que tu m'entends?
Oui.
Alors, en fait, je suis dans une autre salle visio où j'attends le jury qu'a créé Claudio. Donc voilà. Donc c'est pour ça que tu me voyais pas avant. Je suppose que l'autre sera pour tout à l'heure.
Salut Olivier.
Bonjour à tous.
Bonjour.
Olivier, si tu peux, si tu peux envoyer les papiers signés pour la vidéo.
Oui, il me faudra juste la confirmation du nom du président ou de la présidente du jury.
Je vais t'envoyer ça.
D'accord.
Ah oui. Internet, on était à peine.
Olivier, on a un tout petit écho de ton côté.
Et, bah, écoute, dès que je vais couper le son, de toute façon, tu vas voir. Voilà.
Super, merci.
Yeah.
C'est bon.
So I guess I will just do like the introduction in French.
Ok.
Donc bonjour à tous. Donc c'est avec un grand plaisir que je vais présider ce jury. Donc je vais d'abord commencer par présenter les différents membres du jury. Donc c'est la thèse de Maxime Bernard qui est intitulée Haptic Shared Control for Multi-Robot System. Donc on a deux rapporteurs qui ont relu le manuscrit. Donc Francesco Finello, assistant professor at University of Aarhus in Denmark. Ensuite, on a Fabio Morbidi, maître de conférence à l'Université de Picardie Jules Verne, en France. Et on a à distance un examinateur qui est Olivier Simonin, professeur à l'INSA de Lyon.
Bonjour.
Et donc, en local, on a le directeur de thèse, donc Paolo ROBUFFO, qui est directeur de recherche au CNRS. Et du coup, dans l'encadrement, donc ils sont considérés comme invités aujourd'hui. On a donc Claudio PACCHIEROTTI, chargé de recherche au CNRS ici, et Marco Agravi, ingénieur chez Aption. Et donc moi-même, Maud Marchal, professeur à l'INSA de Rennes. Et donc, on va commencer par une présentation des travaux de Maxime. Maxime, tu as 45 minutes.
Thank you for the introduction. So good morning, everyone. Before I begin, I want to sincerely thank all the jury members for being here today, and especially for the reporters for the time you've taken to evaluate my thesis, and for your presence today. So I'm going to present the work I did under the supervision of Paolo GIORDANO and Claudio PACCHIEROTTI, which is called Haptic Shared Control for Multi-Robot Systems. So let's start by defining the topic of this thesis. So a multi-robot system refers to a group of autonomous or semi-autonomous robots that are designed to operate collaboratively within a shared environment to achieve common or distributed goals. They rely on coordination strategies, communication protocols, and task allocation methods to function effectively as a collective. On the second hand, shared control refers to a framework where both the human operator and the robotic system contribute to the control of the robot. The control authority is being dynamically or continuously distributed between the two entities, and the goal is to combine the strengths of the human intuition with the precision and accuracy of robot autonomy. It is especially valuable in complex or dynamic environments, such as assistive robotics, teleoperation, or search and rescue. And finally, haptic in robotics refers to technologies that provide tactile and force feedback, allowing the users to physically feel and interact with remote or virtual environments. So the outline of the presentation is as follows. I will start by presenting related works from the literature. Then I will introduce the first contribution, which is connectivity maintenance with field of view constraints. On the second part, I will introduce a few shared control approaches, allowing the user to control the group of robots with different level of authority. And finally, I will conclude my presentation. So let's start with multi-robot systems. In multi-agent systems, scalability is often achieved through decentralization, which, unlike central system, where a single controller manages all the agents, for a decentralized system, we rely on local communication and sensing, to allow each agent to contribute to the overall objective independently. It can be seen in the nature, such as ants collaborating to reach a distant target, or fishes that avoid predators and lure them with these big motions. So in robotics, decentralization is a central topic because it enables scalable and robust operation, which is fundamental for multi-robot systems. So multi-robot systems can be used in a wide range of domains, such as surgical application or warehouse automation. So on the left, we see a shared control simulation where a human operator is controlling multiple robots in a vascular system. And on the right, we see a warehouse of a Chinese delivery company where robots help the human to deliver packages. So in order to control the system, we first consider a group of multiple robots. In the scope of this thesis, it will be equal daughters. And we will like the robots to achieve certain cooperative tasks without relying on any external positioning system, such as GPS or motion capture, which would provide position and orientation in a global reference frame. So we only rely on relative sensing, in particular on feedback from onboard cameras, which have limited field of view and sensing range. So here are shown the field of view of the cameras. And the agent can sense and communicate with a limited number of neighboring robots. And these sensing and communication interactions are modeled by the sensing and communication graph, represented by the dashed line here. So in the literature, various approaches were explored when it comes to control of multi-robot systems. We broadly define them in two categories: rigid formation control, which requires to maintain inter-agent measurements such as distance, relative, position, or orientation constant. So that's what we see on the example here. Or flexible formation control, which on the other hand allows for these measurements to change over time, which enables the formation to adapt to environmental constraints and task requirements, while preserving overall cohesion. So this example shows flocking, which is similar to the fish example we saw before. To represent and control multi-robot systems, we use graph theory. Each agent is associated with a node, and the edges represent inter-agent communication and sensing. Edges can be associated with weight that will represent physical quantities, such as the distance between two robots. And the graphs are associated with several properties that are useful for analyzing and controlling multi-robot systems. So in this work, we focus on connected graph and undirected graph. So undirected graph means that the existence of an edge between two nodes implies bidirectional connection. And connected graph means that there is a path that exists between every pair of nodes in the graph. So unlike this example where we see two subgraphs, here we have a single connected graph. So we then represent graphs using matrices, such as the Laplacian matrix, which holds on the diagonal the sum of the weight connected to each node, and on the off-diagonal entries, the negative link weights of the graph. By computing the eigenvalue of the Laplacian matrix and arranging them in ascending order, we find the second smallest one, which is called the connectivity eigenvalue, to be positive only if the graph is connected. So this value allows for mathematical analysis of the graph. And we see some example on the bottom where a fully connected graph has a high eigenvalue for lambda 2, a high value for the connectivity eigenvalue. A connected graph still has the value positive, and here the graph is disconnected, so the value is when controlling multi-robot systems, ensuring global connectivity is essential for decentralized application because it's sometimes the main requirements for decentralized applications such as consensus, flocking, leader-follower strategies, or other collaborative operations. And so the connectivity maintenance algorithm enabled the preservation of global connectivity within the team, which makes, in our opinion, robust and essential foundation for any decentralized multi-robot application. And in the literature, for maintaining connectivity, we find two predominant approaches. The first approach are conservative methods, which aim to maintain the existing edge. Some methods allow for the appearance of new edges in the graph. However, no edge can be dissolved, while on the second hand, flexible approaches allow for the dynamic modification of the graph topology, which permits to add or remove edges as long as global connectivity is maintained. In the scope of this thesis, we will focus on the second approach, and in particular, this work introduced by Paolo GIORDANO in 2013. So this strategy is capable of handling complex sensing models and dynamically forming or dissolving interagent links while preserving global connectivity. So we use the cost function lambda2 to have a vertical asymptote when the value of lambda2 approaches the minimum value, and to smoothly decrease to 0 when the connectivity and the AN value increase. And we designed a gradient-based controller that is designed to minimize the cost function v lambda. So by having each agent of the group implement this force, the connectivity AN value is maintained above the positive threshold lambda2 min. So to implement the gradient-based controller, each agent follows the generalized connectivity force. And if we develop the control input for agent I, we see the element of the AN vector V2 that is associated with the AN value lambda2 appearing in the equation. This value and the connectivity AN value can be estimated in a decentralized way using a combination of different estimators. And we also see that if the weights in between the agent and their gradients are designed to be computable from locally available information, the connectivity maintenance law can be implemented by agent I in a decentralized way. Let's speak a bit about haptic shared control now. So grounded haptic interfaces delivers haptic kinetic feedback, which provides the user with information about position, velocity, forces, and torques. The first haptic-enabled teleoperation system were introduced in the 40s, which allowed operators to manipulate radioactive materials from a safe location. But the mechanical linkage required for these systems limited the range of operation, which led to the development of electrically coupled manipulators, such as this device, Phantom device on the right. In the literature, we can find many applications of haptic shared control in many fields, such as the remote operation of robotic arms. So the robotic arms automatically handle different constraints, such as collision, joints, limits, and singularity. And haptic guidance and shared control algorithms simplify the execution of grasping tasks. Haptic shared control has also been applied to a team of drones. So in this work, the authors show how a human subject can be part of a robotic team while being guided through wearable haptic devices to maintain connectivity with the robotic team. So let's dive into the first contribution of our work, connectivity maintenance with field of view constraints. So all previous work in the literature on connectivity maintenance treated agents as point masses without orientation and assume undirected sensing graphs, meaning that if one agent could sense the other, the reverse was automatically true. Our work challenges these assumptions to better reflect real-world scenarios, but introduces significant algorithmic challenges. So we assume each agent equipped with an IMU, a radio communication device, and a calibrated camera with a limited field of view, providing relative position measurement in the body frame of the agent. We consider measurements in the body frame of the agent instead of a common frame. And we propose to adapt the connectivity algorithm to account for this limited field of view sensor. So we need to extend the algorithm to control not only the linear velocities, but also the angular velocities of the agent. So the dynamics looks like so. The connectivity maintenance algorithm requires weights with specific properties. So they should remain constant at a maximum value when the agents are well connected and smoothly decrease to 0 as the connectivity weakens. And finally, the weight must also have a vanishing derivative as it approaches 0. So we introduced this standard interdistance weight that aims to keep neighboring agents within a bounded and desirable distance from one another. So it starts at 0 when the agent interdistance is too small. It increases smoothly to a maximum value of 1 as the distance enters the preferred range. And within this range, it remains constant. And finally, when the range is too far, too great, it decreases smoothly to 0 again. In practice, this helps ensure that the agent remains within an appropriate communication range, and also that the onboard camera can perceive the neighboring agents, avoiding the situations where the agents are either too close or too far away to be sensed. The second weight we introduce is designed on the visibility function that we introduce here. So this visibility function it depends on the cosine of the angle between two directions, the direction of the onboard camera and the direction of the neighboring agent. When this angle is low, the function is high, the weight is 1, which means that when the neighboring agent is near the center of the field of view of the onboard camera, the weight is high. And as the agent goes away, the weight decreases, and we see the corresponding velocity input that we will detail later acting on the robot here. However, this function cannot serve as the weight directly in the connectivity maintenance algorithm because it's not symmetrical. And while we consider asymmetric sensing capabilities, we need a symmetric graph for the connectivity maintenance algorithm. So to ensure symmetry in this interaction, we define the field of view weight as a composition of the visibility function. As two connected agents can communicate together, the relative measurement can be communicated. So we do not need to impose mutual visibility between two agents. And so this design choice allows the weight between a pair of agents to reach a maximum value whenever at least one agent sees the other, which is the case here. However, of course, when two agents are not able to see each other, the weight is 0, but they are disconnected. So they are disconnected. So now the linear and angular control input of the connectivity maintenance algorithm are defined as follow. So we recall that this value can be estimated in a decentralized way. And by developing the gradient of the weight, we observe the appearance of a transition matrix. It appears because we consider body frame measurements, and it depends on the relative orientation between two agents. While some works in the literature demonstrate technical applications of relative orientation measurements between two agents, this task remains challenging when we use only onboard cameras. And this is particularly true for drones because the symmetrical structure makes it difficult to distinguish orientation. So in this work, we propose an estimation method based on the relative position measurement combined with inter-agent communication. Our initial approach is to estimate the velocity of a neighboring robot, so robot J, in the body frame of robot I. Then robot J communicates its own velocity in its own body frame, and the angle between the two velocities here is the relative orientation between the two body frames. However, with this method, we do not use all the information available, and this estimation strategy is only reliable under certain conditions. Specifically, if the robot J is stationary or aligned with the vertical direction, the measured velocity appears, sorry, the estimated velocity appears identical in both frames. And so this method is impossible to use in this case. So we propose a more complete method using all the available information. So psi hat will be the estimation from the previous technique. And by incorporating the angular velocity of the agents that are either measured or communicated, we define a new estimator that has these dynamics. And we can consider two cases. First, when the agents are mutually visible, the product of the two weight, the two visibility function is 1. And so they both measure relative position, and the angle between those two relative position measurements is the angle between the two body frames. And so the measurement corrects the estimation based on odometry only. And in the second case, when only one agent sees the other, we use the method from the previous slide, which corrects the forward odometry propagation However, we also assign a gain that decreases and vanishes when the velocity of the observed agent is low in order to avoid using unreliable measurements. So now that we designed this algorithm, we want to validate it in experimental simulation. So here is a brief overview of the system architecture. We use several ROS2 nodes to process user input and compute velocity commands for the drones. Each drone runs as an individual ROS2 node and can communicate and sense only with its directly connected neighbors. The velocity commands are sent to a genome tree component that simulates the dynamics of microcopter drones, which are the drones we had in the lab. And finally, the drone state is forwarded to a Unity visualization for the user visual interface. So here is how it looks in the video. So on the top left, we provide the onboard camera view of each agent. Here are the model of the agent, and the green cylinder shows the onboard camera direction. The plot of the connectivity and value is shown here alongside the plot of the estimated values. And here we show the number of links in the graph. Here are the two weights we presented just now. So the field of view weight and the interdistance weight. You see the blue arrow, which are the contribution of the weights. The colored links show the connectivity, the value of the weight. So when it's red, it's close to 0. When it's green, it's close to 1. And when we enable the connectivity maintenance algorithm, we see the drone, the weights are increased so that the connectivity AN value rises up to a certain fixed maximum value. Also, we note that it's not possible for the algorithm to create new links only when a drone starts sensing another one, then a link is created and the connectivity and value can increase. So that's why here we reach a local maximum for the connectivity value. And now a user will start to impart commands on one drone. We will see blue arrows that shows the user input. And we will see how the neighboring agents adapt to these control inputs. So here we see that the user is rotating the drone. So one weight decreases, but the agent starts sensing a new neighbor. And so a link is created and the weight increases. You see the green patches is when the user is controlling the agent. And we will see now that, interestingly, when the human is rotating the drone in such way that drone 3 is going to lose connectivity, drone 3 adapts to this input by going forwards to remain in the field of view of the agent 1. However, here the user controls and counteracts the connectivity maintenance force and goes too fast for the drone 3 to adapt, and so the weight is lost. In this control architecture, the user is using a classic joystick controller to control the agents. So here is the plot of the connectivity AN value throughout the task. We also see the estimation values and the number of links in the graph. And more interestingly, here is the plots of the estimation of the relative orientation. So what we plot is actually the difference between the two angles with a trick to avoid having jumps of 2 pi in the plot. So we see that when mutual visibility is acquired between the two agents, so the green patch here, the difference is 0, so the estimation is perfect, because in simulation, actually, the measurements are not noisy. When we start, there is only one agent measuring the other. So here, drone 1 is measuring the neighbor 2. It's using the estimation of the velocity of drone 2 to compute the relative orientation. And we see that the estimation is quite reliable. Same goes for when only the neighbor sees the observing agent. And finally, we see that when no agent sees the other, they are disconnected. So the estimation deviates, is not correct anymore. But as the agents are disconnected, we do not need this value anymore. So let's now dive into the second part, the design of different haptic shared control methods for aerial multi-robot systems using connectivity maintenance. So we want to improve the way users control the multi-robot system. We designed an interface that offers 3 varying levels of control over the group. First, the user can precisely control a single agent of the group. It is particularly useful for tasks requiring fine maneuvers, such as inspecting a point of interest or interacting with the environment. And secondly, the user can select a subset of agents from the group to steer them towards a desired location, which enables flexible local interventions. Finally, we provide control over the entire formation at once, which allows the user to efficiently move the team over long distances. The novelty of our approach lies in the integration of these control nodes with haptic feedback, which offers the operator information about the connectivity of the team. So let's introduce the haptic interface we used. It's a 6 degrees of freedom haptic device from Haption. There is a laser sensor behind the handle that serves as the deadman switch. So it means that when the user is not grasping the handle, both the control input from the user and the applied force on the handle are disabled for security purposes. But also when the user starts grasping the handle, it sets the origin of the workspace at the current position of the handle, just like a mouse when you lift from a desk and put it back on the desk, starts sensing again. So we designed 3 forces to achieve a joystick-like behavior. So here is a slice of the forces with the center, the origin point in the middle. The first force is the dead zone force, in which, inside this zone, the user is not sending any output command. And so this force is designed to help the user remain in this position, just like a joystick, a 2D joystick goes back to the center position with a spring. And this is actually the centering force that is this spring guiding the user back towards the center of the workspace. And the workspace is limited by the workspace limit force that aims to have homogeneous commands and to restrain the user within a sphere. These are the linear forces, but the virtuous device is 6 degrees of freedom, so we design similar forces for the torque feedback. Let's now introduce the control and feedback position for these techniques. So the 3 control techniques are associated with 2 feedback conditions. The first one, where there is no haptic feedback, only the joystick-like forces and torques are applied on the virtuous handle. And the second case is the haptic enabled case, where the user feels both the joystick-like forces and additional forces and torques that reflects the states of the robotic team. By adding haptic feedback, our goal is to enhance the user's situational awareness and to help them better understand how their control input influence the connectivity maintenance forces acting within the team. So in the first case, where there is no haptic feedback, the virtuous handle outputs an output command, which is a linear command and angular command, which is the difference in position between the idle position and the idle orientation of the handle. A control interface that will depend on the control method used will then compute a velocity command that is sent to the control agents. And the control agent follows the connectivity maintenance force as well as the external input from the user. On the other hand, with the haptic enabled case, the same output is provided by the virtuous device. And also the external input stays the same. However, this time, the control interface also computes residual connectivity force input that is followed by the agent instead of the actual connectivity force, which is sent back to the control interface to serve as force feedback, which is added to the joystick-like forces to be applied to the virtuous handle. So all these values will be different depending on the control method we use, and that's what I will introduce now. So let's start with the single agent control mode. So when the operator controls one agent at a time. So the external control input is just a scale version of the command outputs from the virtuous device. And in the haptic-enabled case, the external input is the same. However, this time the controlled agent does not follow at all the connectivity maintenance force, which is instead fed back to the user through the virtuous handle with a scaled version. We conduct a user study for all three control modes, experimenting with different haptic feedback modalities. So the user study consisted of this architecture, where the user were using the virtuous device in front of a flat screen showing the scene that depends on the scenario of this experiment depends on the control method used. And so in the single agent control mode, the user was tasked to sequentially reach objective locations using a specific drone. The goal here is that as the decentralization enables to scale the team, by equipping agents with different sensors, we can also scale the variety of sensor capabilities of the team. In these experiments, we consider 3 types of sensors that are shown using the colors around the drones. And multiple agents carry the same sensor to ensure redundancy. So here, for example, we can say that the green color represents a gas sensor. The red could represent infrared camera to analyze hotspots in a structure. And at each objective location, there is a colored arrow showing which sensor needs to reach this location. During the experiment, the user could only see the agent and the scene and the objectives. And for analysis, we show the connected the weight lines as well as the plot here and the haptic force felt by the user. The gray cylinder shows the direction of the onboard camera of the agents. And we see that the user is controlling one agent to reach the objective. Once the objective is reached, the users change the control drone to adapt to the next objective requirement. And the user was also provided with a top view camera of the scene. So thanks to this user study involving 20 participants, we highlight the questionnaire highlights that the participants evaluated the case with haptic feedback, so in the orange here, to be more intuitive and effective. And we also measure the completion time lower with the haptic-enabled case, which means a better performance. So we can conclude that for this control method, single agent control method, the average operator profits from the presence of haptic feedback. The second control method is pinning control. So in this case, the user has control over a virtual pinning point that is pulling selected agents from the group towards an orbit around this pinning point. The user can also impart orbital control over the pinned agents by rotating the virtuous handle. So the control inputs in the no haptic feedback case looks like such. The pinning point has dynamics, and for the same as for the single agent control, it is controlled directly from a scaled version of the command output from the virtuous device. And the control inputs sent to the pinned drones are actually only linear velocities. The angular motions of the agents are not controlled by the pinning method. And this control input is divided into 2 parts. So this part is the linear action pulling the drone towards the orbit of the pinning point. And this action is the angular, it depends on the angular input from the virtuous device and is the orbit command sent to the drone. So we see on this illustration how the user can control the team. So we see that when rotating the pinning point, the agents are orbiting around the pinning point. So it's not a fixed formation control, which means that the agents are pulled with spring-like forces. And we see that when the pinning point goes away from the pinned drones, they are pulled towards the orbit of the pinning point. In this case, we also allow the user to click on agents to pin or unpin them and control them to select which agents are pinned in the group. And so that's for the control inputs. Now in the haptic feedback enabled mode, the control inputs are again the same, but this time for the haptic feedback. So first for the residual connectivity maintenance action, which I recall is the connectivity force followed by the pinned agents, is a scaled down version of the actual connectivity force. And the force feedback is decomposed into two components. So one component is projected on the tangent plane on the sphere of the orbit of the pinning point. So this component will be fed back to the user as torque feedback. And the other component is projected on the direction linking the pinned agent towards the pinning point. And this is a linear force feedback. So the user study was a bit different from the single agent mode because now we control multiple agents from the group. So this time the objective locations has two colors. So they require two types of sensor at the location. We could imagine in a real world scenario having one agent with a classic camera to inspect the scene and the other having, for instance, here gas sensor to identify the type of smoke. So here is the pinning point. Here is the objective with the two colors we see a bit behind. Once the user reaches the objective location, a new one is designed with new types of agents required for this location. The blue arrow shows the force feedback experienced by the user, but I recall that the user does not see this arrow, they only feel it in the haptic enabled case. So this experiment showed these results. So we observed no statistical difference for the experienced intuitiveness and the completion time. However, the user felt that their effectiveness was statistically higher. So this is the median. This is, sorry, the star is the median and the line is the median and the star is the mean. So we think that the user felt more effective with the haptic force feedback enabled because they could feel the resistance from the pinned agent, and so they could understand why sometimes the agents would slow down, which is in fact to maintain a desired distance with the other agents. And the last control mode we introduce is the centroid control mode, where the user imparts command on the whole team at once. So the actual position of the centroid of the group is not actually controlled. It's computed as the average position of all agents in the team. But while we do not control the centroid's position, we do control its orientation. So we define a mapping matrix for this control mode because we provide 7 degrees of freedom of control over the team. So the 3 linear motions, the 3, so panning, tilting, and orbiting, and scaling motion. So because the virtuous handle only has 6 degrees of input capabilities, we need to design a way for the user to impart 7 degrees of control. The user inputs is the combination of the mapping matrix with the inputs from the virtuous device and the vector of gains. We design the centroid control matrix, the centroid control matrix, which holds the BP, which is binary variable set to 0 or 1, and it is used to switch between pan tilt control and scaling control of the team. Finally, the control input for one agent is shown as the product of the centroid control matrix and the user inputs. So here are shown the degrees of control over the team. This is the scaling motion. We will see the pan tilt motion, and of course the orbiting motions and linear motions of the team. To provide force feedback in this control mode, we decompose the connectivity maintenance force into 2 components. So the first component aligns with the direction of the operator's inputs and is used to generate haptic feedback, which guides the user to maintain connectivity. In practice, connectivity is most impacted when the user scales up or down the formation. So that is when the user will feel more haptic feedback. And the other part is the residual connectivity force, which corresponds to the remaining directions not controlled by the operator. So as the operator cannot act on these motions, it is sent and followed by the agents as the residual connectivity force. So with this design, if the user strictly follow haptic guidance, the agents receive the full connectivity maintenance force. So in this case, the experiment was a bit different. The users were tasked to discover an unknown environment within a limit of 5 minutes, to highlight the use of the scaling motions. We also placed areas to avoid in the environment, so these red cylinders. When entering these cylinders, the users would receive a penalty. So the discovered environment increases, as we see on this percentage here. This was shown to the user. And we see that the user scales up to discover as much environment, then scales down the formation to avoid areas to avoid. In this scenario, the user only had control over the orbit, the scaling, and the linear velocities of the agent, but not on the pan and tilt, because as we see, it's a two-dimensional problem in this specific scenario. The poll results show that the user felt the haptic-enabled mode to be more intuitive. However, there is no statistical difference for the perceived effectiveness, but instead, the experiment shows that the user discovered more area in the haptic-enabled case. So to sum up this user study, we showed that in general, providing haptic feedback to the user achieved better results than providing visual feedback only. Not only did the user feel the control mode to be more intuitive and efficient in most of the cases, the mission objectives were accomplished faster or with better performances. We also think that with trained operators, the performances of haptic feedback methods could overcome the baseline even more. Let's now introduce a use case of these control modes. So in this scenario, the remote user can switch dynamically in between the different control modes. So it is using the same system as for the user study. I will skip a bit the introduction of the video. So we see that at the beginning of the experiment, the user is controlling the whole team with the centroid formation to read the centroid control mode to reach a distant location. Once the location, the mission area, let's say, is reached, the user can switch the control mode dynamically, as we see here, in order to control a single agent to scout objectives area. So the other agent will maintain connectivity with the control agent as introduced. And once the user reached the point of interest and analyzed what are the objectives at this specific location, they can use the pinning control mode to select a few agents from the group to achieve the task required at this location. So we will see a bit after. Here, the user switches to pinning control mode, so the virtual point appears again on the center here. And using the mouse, the user can click on different agents to select them and start controlling them using the pinning control method. Okay, so to conclude this presentation, I will do a summary of the contributions. So the first two are that we consider connectivity maintenance with body frame measurements and limited field of view. We also propose a new relative orientation estimation method. This work was published in IROS. Then on the second part, we showed multiple haptic-enabled shared control methods, and we did a user study to compare these methods with the haptic-disabled cases. And this work is under review at Transaction on Human-Machine Systems. Finally, all these theses led to the development of many software tools that will hopefully be available to the community soon. The limitations of this work are that the current haptic modality are limited to force feedback, while we could improve the user information feedback using vibrotactile or other kinds of haptic feedback. The connectivity maintenance algorithm does not account for the pitch and roll motions of the agents. So in the case of quad rotors, when accelerating, the agents are panning and tilting, which can change the field of view and the visibility of the camera, which is not accounted for in this algorithm. So aggressive maneuvers might lose the sensing make one agent lose its sensing capabilities. The recovery from the loss of global connectivity is not possible with this architecture. There is no line of sight occlusion avoidance capabilities. And also, it's impossible to add or remove agents from the group. However, this limitation has started to be addressed in the team. And finally, some perspectives, which cover, of course, covering the limitations or having real-world experiments. We also think that using this algorithm as a baseline for any decentralized applications, such as coverage or collaborative SLAM, could be useful. And finally, I wanted to introduce this challenge, which is the DARPA challenge, where agents and teams were tasked to find and locate artifacts in underground and subterranean environments, where communication with the external world is really complicated. So in this case, maintaining connectivity with the team allows for a remote operator to access distant robots that are deep into the tunnels through an ad hoc network, so communication passing through any agents. So here we can imagine a team with heterogeneous robots, such as drones scouting the environment, legged agents interacting with the environments, and tracks robots that are designed to carry payloads and drop communication relays points. And so that's the conclusion of my presentation. I thank you for your attention.
Merci. So thank you. So let's now start the questions. So we'll start with the two reviewers. And we'll start with the one with I'm sorry, father from here. So let's start with you, Francesco.
Thank you. And thank you, Maxime, for your presentation. And all firstly was very nice and inspiring to read that your work, and really like your presentation. It's actually very impressed also from the design of the experiment and the variety of the scenarios. That's very, very, very good.
Thanks a lot.
So I was curious to explore a little bit more about your let's say perspective and angles on this work, and also of course from the scientific and technical point of view. For example, it's in general you introduced very much with a nicely description many elements that are present in the literature. I was also curious about the description on, for example, you have done regarding the global sensing and using instead let's say more respect to the local sensing. And I was wondering, do you see any, so how do you relate the diverse typology of sensing for robotics, for example, in let's say realistic scenarios, or close to, for example, you've shown the DARPA challenges. So how do you see the differences between these type of sensing systems in a real scenario? What is your perspective? What is your point of view on that?
So in my opinion, global sensing is really strong for indoor environments and experiments. So in the lab, for instance, we have motion capture systems, which provides measurements that are really, really precise. However, in real-world scenarios, we can imagine, like in medical robotics, where the environment is controlled. Here, having global sensing can also work for micro robotics applications. But for instance, in the case of this challenge, which I think highlights the most the sensing limitations, because it's a subterranean environment. So even here, this agent might not be able to communicate with this one because of the thickness of the wall. So in this case, global sensing such as a GPS or GPS is not at all reliable, and local sensing is really important, I think. And also, in my opinion, the most useful application of this work in a technical way is using it alongside the collaborative SLAM algorithm, because then the agent can collaborate and remain connected while building a map of the environment, which is based on local sensing capabilities. And for any distributed algorithm, having a globally connected graph of the communication graph is mandatory. So that's what I think, yes.
That's very interesting. And it's do you see any complexity in the swap of the two type of sensing in the same system scenario, or it's a strategy that could have been designed beforehand, so you know before it's more feasible in general to look what is the scenario and then approaching the one specific type of sensing, or is there any chance to also to have a relatively easy implementation in a swap system that can interchange between local and global sensing?
So in my opinion, this work and kind of, I'd say most of the work that are designed to use local sensing can easily work with global sensing. And actually in this scenario, of course, it was in simulation, so I had global sensing, but I was simulating local sensing by computing the field of view of each agent, computing the relative position in the body frame, and then providing the agents with these measurements. But we can think that, we can imagine that instead of doing all this, I just provide directly the position of any agent, and then I compute which are the actually connected agents using the weights. But on the other hand, I'd say that having a system that is designed to work with global sensing and making it work with local sensing without any algorithmic modification is close to impossible, I would say. It would require many algorithm changes.
Thank you. So if you would like to identify some measure gaps or research gaps, actually, I'm referring to, because actually this is actually a huge topic, right?
Yes.
You have identified very specific scenarios, and of course testing parametric doing parametric experimentation. That's how it is. But did you had the chance to let's say explore if for example there is, let's say, a sort of rating or classification about major research gaps in the area of multi-agent systems? So did you get inspired from the literature, from your research, to go towards this particular type of problems, let's say? Is that because it's more diffused, or is it just because you liked it?
I think it was, so I have an engineer degree, so it was mostly technical challenges that attracted me in this work. And there is not much work. There is the multi-robot system group in Prague that does many decentralized applications that are really technical, and they actually provide a nice way to measure relative orientation between two agents. But as you said, all those techniques are inspired to be close to real-world implementation, to be realistic. And I think that's something that still is lacking in the literature, having a real-world experiment with real decentralized system. And yeah, I think that's the research gap.
Yeah.
I'm not sure I understood the
So,
way.
yeah, it's let's say exactly the point I was meaning, in the sense that I was curious basically to know if, for example, you had inspiration, let's say, from aspects, open aspects, or let's say, and aspects that are not research in literature, that, okay, oh, I should go in this direction, because I think
Yeah,
this
I mean,
is
what drove me was really having an approach really close to reality. And actually, I think bridging from this simulation scenario, when I developed my work, I tried to remain as close as possible to real-world implementation. And so having real-world experiments with the actual software architecture should be really simple, because we use ROS2, and so these are standardized messages. So instead of sending the velocity command to a simulated agent, we can send it to a real agent. And we started working on this in the team, having abstraction of the hardware we use in the team. So independently on which agent we control, we can use and control it with ROS2. And that's what drove me along all the way through the thesis to think about this scenario where we could imagine huge drones that are capable of communicating through 4G or a satellite, and smaller drones that are only capable of communicating locally. And so these drones, these huge drones, would serve as relay. And because we maintain global connectivity, the remote operator could still oversee the entire team using different techniques to reconstruct the environment and the position of each agent in the team.
So looking forward to the continuation with the
Hopefully.
and the prototype system. That would be very, very interesting. Then I was wondering, let's say, going a little bit more into the practical aspects. Let's say, is so visual haptic feedback in shared control is, they are let's say, often, let's say, winning combination, but not always, let's say. And you also mentioned in your manuscript that, for example, visual feedback is not always possible to use, or in some cases also not very helpful, because you need to see, actually, you need to have your field of view, or having also cameras, or in, let's say, in virtual scenario, you need to have a, say, visual perspective on that. I was wondering, do you have any, what are your what is your experience in terms of, let's say, researching around the visual feedback provided by, for example, visual cues, or like or maybe augmented reality scenario? Have you had the chance to visualize or compare some of works in literature in that sense?
Not really comparing work from the literature, but this work uses visual feedback and is actually using Unity to be adaptable to virtual reality. Without formalizing it, I imagined different applications for providing visual feedback. So for the single agent mode, for instance, the user could, because we reconstruct a virtual scene, even in real environments, we could use a way to reconstruct the position of the agent in a shared frame. So showing virtual twins to the operator. And so if we use virtual, or even so if we use virtual reality, we could attach the operator view to any agent, or provide a third-person view, as we did for the experiments. But however, of course, visual feedback only sometimes is better than an abstract way to provide visual cues, such as the control of first-person view drones, where the operators are doing really agile maneuvers, and they need to have the visual feedback as fast as possible from the onboard camera of the drone to effectively control it. Yes, that's it.
Yeah, it's would that be also inspiring, maybe also for some future experiment as well? Maybe like trying to have this cross comparison between maybe condition that can be provided maybe with also let's say augmented information visually versus something that would be very very intriguing.
And one goal was also to use the cave system, the immersion room we have in the lab, which is a virtual environment in 3D, so a cave setup. And using this with haptic feedback could really immerse the operator. This has also, of course, to be researched and proved using user study, for instance. But it's a nice future perspective indeed.
Yeah. So, regarding the type of interfaces that you selected for example, also for the experimentation, especially in the shared control scenario, you utilize mostly, let's say, mostly grounded device.
Yes.
You also mentioned wearable haptics as a part of a type of stimuli, so the type of device that can provide stimuli for the skin. So I was wondering is how did you select the type of haptic cue in this sense? So it was what was your strategy to approach? Let's say I want to use the grounded interface providing kinesthetic feedback and force feedback. So why did you decide to explore this direction and particular?
From the literature, I identified that wearable haptics were mostly useful when the user had to be guided to move in an environment. So as we saw in the introduction with the scenario where the user was part of the team. And in my sense, grounded haptic interface can provide force feedback, unlike wearable haptics. So kinesthetic feedback, which is, I think, one of the most intuitive way to provide information to a user, especially in those scenarios. But however, the Virtuos device, which we chose because we had one in the lab and it's really well suited for these applications, can be equipped with a different handle, for instance, which could provide vibrotactile or electric stimuli to even more improved feedback sent to the user. Let's say the handle could vibrate when a new agent is connected or other kind of information that would be task related.
Very interesting, because that's actually one curiosity, because, for example, sometimes it's also interesting to see how you can obtain maybe different results, also exploring maybe, for example, the portable device, or let's say portable haptics or controllers that can vibrate.
Yeah.
For example, for this scenario, and that would also be used, for example, for alerting you about you cannot build, I mean, big gradients of big variations of sensation, but still that would be also interesting to explore. Did you evaluate that certain point, or and then you decided to point the attention, especially on the force feedback, or is future work? What
it could be interesting also. I know in the literature there exists some look-alike of classic controllers where the joystick can provide haptic feedback to the fingers. So this kind of haptic feedback is, of course, as you said, less strong than a grounded device. But indeed, it could be interesting, and I think technically easily adaptable to this feature. But however, because it's 2D joysticks, it would have to be modified in order to. But it would just be maybe the mapping matrices that will change. So we did not explore it, but it could be explored quite easily.
Thank you. And in relation to that is it's so for the strategy adopted for the force feedback is like a more attractive or repulsive force that you use, and why in that case? Why did you choose?
For the force feedback.
Sorry, for the sharing, for the shared control scenario, for example.
So for the force feedback applied to the virtuous, so it was mostly attracting forces towards the center of. This was a passive force that was always present, and this was not the actual force feedback, as you understood. And the actual force feedback was related to the connectivity maintenance force. So most of the time it would pull the user towards the team. So because most of the time what the user does is move the agents away from the group because they want to move to a location. And so the force feedback will, most of the time, counteract the user. So attract them in the opposite way of the control input. But it could happen sometimes that pulled forces, I mean, the opposite forces would arise in case where a new agent would be sensed by the control agent, and so the weight would be decreased, and so the force would pull the agent towards this newly sensed agent.
So the decision of the policy, did you had let's say the decision to explore because of let's say literature inspiration, or maybe because it was more intuitive, let's say, for the user also?
Some cases were inspired by literature, and some were intuition that the user would experience, because many choices in this scenario and experiments were from intuition, such as how to position the camera, the view. All those factors could be experimented in a user study, but it was not done due to time constraints.
Sure.
And so this kind of haptic feedback policy could, the choice of those policies could also have been experimented in a user study.
Yeah, sure. And it works very well, as I see. So it's a good intuition in that sense.
But I think in the video game literature, for instance, we could maybe find many inspiration for this work, and that's actually where I found inspiration, such as when the operator is controlling one agent and orbiting, how should the camera follow behind the agent? Should it be really strongly attached? And so any noise on the orientation would shake the camera, or should we have a slacking factor? And all these were from personal trials and experiments to identify which are the best way, or in my opinion, and not tried through a user study, to provide the user with visual feedback. And the same goes for haptic feedback, such as the constraints in a sphere. All those were choices from literature and from personal intuition.
Yeah, and that's perfectly fine to stabilize hypothesis. That's fine. And it's I was wondering also about the regarding the connectivity, let's say, model that you have created, and also the algorithm that you have used to identify the level of connectivity. I was wondering is, did you identify any, let's say, or let's say, what are the measure limitation, for example, connected to the delay for the group? So, for example, you realize that so the algorithm realized basically that there is maybe a reduction of connectivity, but does the delay affects also the overall performance of the group in let's say into reconnecting the drones, or maybe you decided to stabilize this part and say, okay, let's keep this constant and focus on the other parameters. So what has been your strategy there? Also regarding the delay of the information you get from lose or increase of connectivity.
So the delay from the information was quite low, because in ROS2, when you run all the components on the same computer, which was the case here, the communication is actually shared memory. So the communication delay was really low, which is not really realistic, but it's especially hard to simulate realistic communication with ROS2. And we did not try to add communication delay that could, or sensing delay that could indeed lower the efficiency of the algorithm. However, we observed that, as you said, the algorithm takes time to catch up with the connectivity loss, let's say. And when controlling a single agent, we had to tune the parameters in such way that we don't have this kind of motion where you pull a single agent away. So let's say 2 or 3 connected agents starts to follow it, but then are pulled backwards by the other agent that starts to flow. And so you could have this kind of let's say I don't know how to express it, but this kind of motion. And on the force feedback, it would be felt like sinusoidal force for the user. So we had to tune the gains, the control inputs, and all the system to minimize this. One way was to have a slope that was not too steep for the interdistance weight. So when the agent starts to go away, the weight decreases, and it does not decrease too fast, so that the agent will act really strongly to the connectivity loss.
Okay, that's very interesting. Actually, that's the delay is a never-ending fight for when you have control situation. So another curiosity that I have while reading your work and listening to your speeches is about the potential, let's say, technology limitation that can be on board of the drones. So, like, of course, it's there is a specific field of view that is precisely parameterized in simulation, and also sensors that distance sensor that. But what is your let's say perception, or let's say feeling about how those aspects that are theoretical in simulation can be then transportable in real scenarios? Because basically you have a sensor that, let's say, this measure 0 to 4 meters, for example, and but then you have noise, you have problems of interference, you have many troubles in use ultrasound sensor, for example. So what is your perception about this?
So in a real world implementation, I think you would have to constrain to define the weight in order to, for instance, for the field of view weight, you would not define it as the actual field of view of the camera, but instead the field of view where you are sure at a given percentage that the drone would be sensed within this field of view, or same for the distance weight. And actually the way we designed the algorithm is done so that it can be achieved to have different weight configurations for each agent, as long as the agent knows the configuration of their neighboring agents. So what I mean by this is that we could have a team where some drones have wide field of view camera, some others have a shorter field of view. And I actually tried, without documenting it, an experiment with a blind agent. So this agent could not sense the neighbors. So it will be the case, for instance, where a human operator will be in the team. And so the neighboring agents would always compute the visibility function of this agent would always be 0, because it has no field of view. And so to remain connected, it means that it has to be sensed by neighboring robots. And such applications, I think the way of designing the weights being so, of parameterizing the weight being so large, so many options, allows for real-world applications that can be adapted.
And that, do you think there is, let's say, a chance or could be inspiring or interesting or not? Say, sort of, is there a sort of novelty, let's say, in also trying to explore, let's say, to simulate, let's say, additional noise or potential camera effect on the
of course, it will be interesting to see how the algorithm reacts. I think that the objective will be to really minimize the noise using filtering techniques, tracking techniques. But of course, it will be really interesting to see how the algorithm reacts to measurement noise, because in the first experiment I showed, the drones were simulated with noise on the IMU measurements, on the dynamics of the agents, but not on the measurements. And I actually never experienced with noisy measurements, and that's also a limitation of the work and something that would be interesting to investigate with. I think that for slow, steady maneuvers, it would be fine for the algorithm, but that's just intuition, and it will need to be experienced with.
It was just a curiosity, because it's of course there are many different aspects and angles that are could be explored in this scenario, because as I said, it's very interesting and open, let's say, to many.
Yeah, but it's true that distance measurements from onboard camera are sometimes noisy, so it's true that having these experiments could really help identifying what kind of problems we could face.
Yeah, exactly. Absolutely. And the lights illumination could also have potential. Do you have?
One.
Oh, okay. So, yeah, I just then I just can have a coffee later. So,
It's together.
It's okay. Let's say jumping, let's say, a little bit more into the final thing aspects. Let's say you mainly mention, let's say, not many, but you mentioned several different aspects, but regarding the applicability of the work, but mainly medical and transport application, for example, for multi-agent system, it's something that is very interesting and explored. Do you see other aspects, for example, in maintenance operation, for example, do you see any future, or how close is the technology and the algorithm application to maintenance process, for example?
For maintenance, like for instance, for electrical cables.
Exactly. Yeah.
Yeah, I think applications of multi-robot systems in this kind of scenario could be interesting. In the literature, I think most of the time it's explored with single agents. I know that the Czech university did, because I did the summer school there, and the final experiment was to inspect power lines using multi-agent systems. So of course, this application could be of interest, mainly for redundancy purposes, and because also we use quadrotors. So if there need to be payload carry, of course one agent is limited, so having multiple collaborating would be interesting. Yeah.
If I may just have a last one. So what's the next step? So it's where do you see the next let's say open problem to solve in research for this experimental scenario that you have?
So for this particular work, I would say that it's combining with other decentralized algorithm. I think that's the main goal because, as I said, we ensure global connectivity, but it's not the main task of a multi-robot system. So having tasks such as collaborative SLAM, I know I say it a lot, but I think it's really a cool application and it's still a hot topic in research. I think it's the main topic to address. But however, having real-world experiments and providing more haptic through different modalities, such as tactile and other cited, I think these also are really interesting subjects for this research in particular.
Thank you.
Thank you for the questions.
Thank you. So let's continue with the second reviewer. So Claudio.
Thank you very much. And so first of all, I would like to thank the supervisor for inviting me. So it's a pleasure to come in here. And also I would like to, I really enjoyed reading your thesis. I also enjoyed the presentation. There was very nice video illustration and so on. This really add new useful information to the manuscript. So I will start with a general comment and then I will maybe enter a little bit more into the details. So as my colleagues already pointed out, it will be, the simulation that you did are really interesting. They show very well the idea and the results. But then the question is, okay, the simulation are realistic, but then what happens in a real world? Especially, okay, if you have, Francesco already mentioned the problem of delays, the problem of noisy measurements, especially outdoor. So it will be very interesting to see if actually the algorithm that you propose are actually robust to this kind of noisy measurement. So it would be interesting to investigate this point a bit more in the future and do also some maybe simple experiment with a couple of robots just to see what's happened. Yeah.
We started developing using Intel depth camera and a LED ring of addressable LEDs to have different colors. We're starting experimenting with a way to identify both the relative position from the camera, but also the identity of the measured robot, which is sometimes overlooked in the literature. So we had really early results, not on board drones, but we didn't try it in the actual scenario. And to cover for this relative position and orientation measurement, there is I'm going to show it because I prepared a slide for it. There is you saw it in the manuscript also, the system from the Czech University, which in this case, they use 360 sensing, 360 degrees of sensing. And this in a real world application, because it uses UV emitting LEDs that are not measured in, there is no UV emitting object in the world except from the sun. And so they are able to have really reliable measurements with this system. And I think it will fit well with the algorithm I presented.
Also, okay, so then I have a more specific question. So in your slide 16, you mentioned that you are modeling the group of robots using graph theory. And for example, here, and so you only mentioned undirected graph. So
yes.
Here you are only referring, as far as I understood, to the communication graph. Because
yes.
If you consider the visibility part, if you have a camera, it would be more natural to model this as a directed graph.
Yes.
Okay? And so what you mentioned here, also the computation of the feeder valve is for the communication graph. Is it
so
correct?
It's also for so the sensing graph is directed, but with the trick to make it symmetric, to make the weight symmetric, the graph we consider is undirected, both in terms of sensing and communication capabilities, because we assume that when one agent is able to measure a neighbor, they can communicate the measured value. So this, in our opinion, renders not the actual technically sensing graph, but an abstract sensing graph undirected.
Yeah, because the feeder value of a directed graph is not necessarily a real number. So you
yes, exactly. And we need a real number for the algorithm to work.
Okay. And then I have a couple of remarks about the, also the first question was about you mentioned that you need an estimator to estimate the components of the feeder vector.
Yes.
And so you mentioned quickly in the manuscript that you are using a PI average consensus estimator. The question was why this estimator in particular. There are many other estimators that have been proposed in the literature. What are the rationale behind this?
I selected this one because it's the one mentioned in the work I based my work on. So the paper, this one.
Mm-hmm.
I did not explore other techniques, but in the team, other techniques are being explored, such as learning-based methods to estimate this value. So it could be of interest to try these methods with the algorithm.
Because for the PI estimator, there are some limitations of the kind of signal that they can follow. If it's like a ramp, it's okay, you have a steady state, zero steady state error, but if you have, for example, a sinusoidal or more complex signal, you don't have any guarantee to have a zero error.
Yes.
So that's why more sophisticated
there is a
distributed estimator being proposed in the literature.
A strong hypothesis from this estimation method is near hovering state.
Mm-hmm.
So that's why when the agents are moving.
Okay, so another question was about the sensing assumption. This was slide 25. What you put in the slide is a bit different compared to what you mentioned in the manuscript in section 3.2. In the manuscript, you mentioned that each drone only need two sensors. A camera-like sensor with a limited field of view, and a range sensor that has 360-degree field of view. But here you mentioned only a calibrated camera, and so why this difference?
So in the presentation, I wanted to really focus on the connectivity maintenance scenario algorithm. And in the paper, the introduction of this 360 low-cost sensor is to ensure collision avoidance. Because of the limited field of view aspect of the camera, we cannot avoid collision efficiently. So the agents would need to be equipped with such as a laser range sensor to identify how to avoid obstacles and collisions. And also, I did not present it here, but this other sensor is not used in the connectivity maintenance algorithm, but instead in a reactive controller, which is just when the distance is too close, too short, the agent will be repelled from the measured obstacle.
Yeah, because also in the when you answered the question of my colleagues, you also say that you got distance measurement from the camera.
Yes.
But if you have a monocular camera, how can you get distance measurement?
So we do not assume monocular cameras. We assume depth measuring cameras, such as Intel RealSense. Direct measurement of distance from monocular camera is not possible, but it can be estimated, or it can be estimated. There is also a work in the team that focused on this, using only monocular cameras, rebuilding the position of agents in a shared frame from only local body frame measurements.
Okay. And also here you mentioned that you need a calibrated camera. Is it possible to relax this assumption? Why the camera should be calibrated?
Because I mentioned a calibrated camera because for measuring the distance, you need to calibrate the camera, I would say. It's like from the experiments I did with this kind of camera, if it's not properly calibrated, the distance measurements might be...
if you consider a stereo system, calibration means the extrinsic calibration, maybe.
Yes.
But even if it is a monocular camera, even if it's calibrated, you still have a scale ambiguity, so you cannot not estimate it.
Yeah, of course. A monocular camera is not able to measure the distance efficiently.
Okay. So another question was about the orientation estimator. It was slide 35. So I enjoyed the way you presented it, you explained the idea behind this estimator, and it seems to work as expected. The question is that these are non-linear estimator. You have some sinus functions, etc. What can we say in terms of stability? Did you try to find maybe a Laplace function, study what are from a theoretical point of view, what is the property of this estimator?
I did not analyze the stability. I cannot really say more about this.
Because another problem is that usually if you have a nonlinear estimator, you are not sure that the convergence is a global convergence, okay?
Yes.
So maybe if you are too far away, if the initial condition is too far away, maybe you have no guarantee of convergence. So did you experience in your experiment any problem like this, or sometimes the estimator didn't work, or some configuration, or it will always empirically give you good results?
So we showed in the first contribution that the simulation, the estimation works. However, in the second part, we do not use the estimation method. So apart from the first few experimental validations, I did not experiment that much with the estimation. We see here on the beginning that it's the error is constant, and it starts converging at this point. And actually, this is a case where the algorithm cannot converge, because it's a case where the error at the beginning is not zero. And if, in this case, I recall that it's the case where we estimate the velocity of a neighboring agent. If this velocity is either zero in the body frame of this agent or the body frame of the observing robot, or if it's aligned with the vertical axis, then the algorithm can never converge. However, in terms of mathematical analysis, I cannot explain more.
Also, in the previous slide, we can see on just right after the red band, the green band, sorry.
Yeah.
You can see that the error tend to be large. What
Yes.
happens there?
So here there is the new link that is created and quickly disappears. And so the time for the algorithm to converge explain this error, which these are the plots of the estimated value on board the drones.
It's why we don't have the same phenomenon at the end of the second band, the second green there.
I don't. This error is not related to the green patch. The green patch is when the user is controlling. It's really related to the addition and disappearance of links, and having only one link, because the estimator works on neighboring information. It's based on a consensus estimation. So when a new link is added, new information is received for the estimation. And when a link disappears, the information disappears. And so this jump is really because of the quick appearance and disappearance of a link within the graph.
Okay. So then in the last part, the second contribution, I have a few questions about the different modalities. So for example, when you presented the pinpoint modality, you mentioned that this work for any number of robots, but in the experiment that you did, you only considered 2 robots.
Yes.
Why, if you have 3 robots or more?
So actually, it works for any number of robots, but we pull the agents toward the orbit of a sphere. Because, of course, if we pull the agents directly towards the point, then having multiple agents trying to converge to a single point would make it would always have, for instance, for the collision avoidance controller, repelling forces. So actually, in reality, having as much as we add drones to the pinning control architecture, then it will be very cluttered around the pinning point. And in this simulation, I only considered 2 drones because I wanted to show that the control method is working for more than one agent. However, I didn't want to oversaturate the user's visual feedback, such as for the objective location, for instance. If it would need 3 types of drones, for instance, it would start to be a bit more complicated to have a scenario that is easy to understand for the user, because the user study was conducted actually at once for the user, so they will fly 6 times, twice for each control method. So I had to keep it quite simple to.
Okay. And also in the equation for the feedback force, and so J here is the number of robots. Is N capital N or is another thing?
So in this pinning method, it's J because J is the number of controlled agents. And in I saw that there was a comment about this on the thesis on the pinning and the centroid control. Here, at first I put N because N is the number of agents in the whole team, which is equal to J in this control mode.
Okay. And also for the first 2 modalities, single agent and pinning, how do you define? I mean, when you have a target location in which you arrive, what is the condition that you have to say, okay, they arrived at the target?
So when I designed this algorithm, the way I did it is having a ROS2 node that simulates the objectives. So this node will know the sequential objective location, the radius of the area, and detect if the drone within this area is of the appropriate color. And for the centroid method, where there was the areas to avoid, I tried a new technique, which is using Unity collision detection. So when Unity detects a collision between the cylinder and one of the agents, it would notify ROS and show the user a red screen.
Yeah, because for the centroid, you don't have a target location.
No.
The user just to explore the environment.
Yes.
Just a kind of coverage problem.
Yes.
While for the other 2 modalities, you have a target location. So, for example, in the single agent modality, if this agent arrives at the target location, that is done.
Yes, exactly.
The condition that you consider.
And this could have been done from the Unity visualization directly, but at that time I did not have really much experience with Unity, so I did it from ROS directly.
Okay. Last question in the interest of time. I have other curiosity, but maybe I will ask you later. Last question was about the assumption about the model, the dynamical model of the drones. So you consider only a kinematic model as a kind of 3D unicycle model, let's say. And so you are not considering, as you also put in the conclusion, the roll and pitch angles. And so the question is, so what happens if we consider a C6 degree of freedom dynamical model that is also quite used, quite used in the literature. And also another question was about, so you have this model, this for the degree of freedom kinematic model, but then in your simulator, the model that actually was considered was not exactly the same. You mentioned that you have more like a double integrator with some limited acceleration. And
for the simulation.
For the simulation. So how can you comment a little bit about all these assumptions of the
yes,
model?
Sure. So because we follow the connectivity force, velocity control inputs were sufficient to have effective results. It was shown in the literature and in this work. So that's why we consider only velocities and not acceleration models. But however, we didn't want to be we wanted to keep a realistic approach, and so that's why we simulated double integrator dynamics in order to have a maximum value for the acceleration of the agent. Because of course, maintaining connectivity when the simulated agent can have infinite acceleration on the orientation, on translations, it would really simplify the model and the assumptions, and we wanted to relax the assumptions and experiment with limited capabilities.
This assumption of bounded acceleration, you can do this assumption also with the full 6 degree of freedom dynamical model. So.
Yes, of course. Yes, in terms of limitation, considering the 6 degrees of freedom, I think it would need, of course, more algorithmic changes. But because anyways we used the PIS estimation, we had this already underlying assumption that the agents are in a near hovering state. So the roll and pitch would be not too strong so as to compared to the U orientation, which would of course really impact the.
Yeah, the problem is you mentioned in the thesis is that in terms of visibility, if you have
of course,
pitch, there could be
problematic. Of course, it could be addressed in future work.
Okay, thank you very much.
Thank you.
Thank you. So now let's continue with Olivier.
Yes, thank you. Could you hear me?
Yes.
Yep.
Okay. Thank you very much. First, I would like to say that I'm sorry to be not with you this morning, but I would like also to thank the supervisors for the invitation to participate to the jury for this nice work. Also, before to start with my question, I would like to say that it's always a pleasure for me to have an ancient student at INSA Lyon that have continued with a PhD and today defending his work. So it's also always a pleasure. So first, I would like to say that I appreciate a lot the presentation today, Maxime. I think that you present and propose a good overview of all your work with good illustrations. And also, as in the document, I think that was with pedagogic approaches to present all this work. I would like also to underline another point as a remark, is that for me, presenting a work that combine several domain problems, which are multi-robot system, shared control, and haptic integration in such system. So for me, it's something more, I think, rare, and I appreciate that you embrace all these 3 points together. So that's very interesting.
Thank you.
So now I go to my question. So I look on my notes. Yes, maybe I would like to first come back to the assumptions about the way you can measure the relative position or orientation. So once again, it's about this assumption. Even if it was already discussed with my colleagues. First, I would like you clarify for me the assumption that you combine vision and communication, in particular for orientation estimation, and it's for only the orientation that you combine both, and you use only cameras vision for distance evaluation. That's correct or not?
So the camera vision is used for the relative position measurement. So not only the distance, but also the direction of the neighboring agent. And the communication assumption is not only used for the relative orientation estimation, because in a technical point of view, the agents need to evaluate the weight with their neighbors. And so in the case where they cannot sense a neighbor, they need to know the relative position between them and the neighbor if the neighbor is sensing. So the communication is really underlying and going alongside the
Okay,
sensing.
so for all, okay. So, okay, thank you for this clarification. So you need both. Always.
Because this is the way we have the undirected graph for both the sensing and communication assumptions.
Okay. And about your assumption for for the vision and cameras you're supposed to use, and to be able to measure this speed variation and or rotation. Yes, I was thinking about how you can validate, in a sense, such assumptions with existing solution or not. I think that you provided some answer in the discussion with Fabio. So I think you already answered to this question of giving some existing hardwares to do that. So I'm not sure that you want to add something about this specific point or not.
Well, I know that some work tried using learning algorithm or other methods to measure the relative orientation, but without visual indicators on a quadrotor, which is really symmetrical when rotating. It's really hard, and so that's why I introduced this technical solution from the Czech University, which I think is really nice. They use like the blinking LEDs to know which part of the agent is being observed. They even have more recent work where the blinking of the LEDs can be used to communicate visually with neighboring agents. So this work, I think, is really interesting and really improves the technical solutions for this kind of measurements.
Yes, I know a bit this system. Yes, you can communicate with light system, but you can also directly visually evaluate the state, the pose, and probably the rotation or even rotation speed. But it's not clear for me if they can evaluate more. But I think it's very good approach. Yeah. Oh, you have some supports?
Yeah. So from this illustration, this is just an idea of their system. We see that they say they measure the distance between the LEDs, the LEDs, to identify the relative orientation, but this is not sufficient because from any side of the agent, the distance could I mean, it's not sufficient. That's why they use blinking LEDs as well, because then the LEDs attached on the different arms, so either on an hexarotor or on a quadrotor, are blinking at a different rate. And so the camera knows which side of the agent is being observed.
Okay, to disarm with the eyes. Okay. Maybe another question about your approach now. It's not clear for me about the idea of mutual visibility. So for visual visibility, you need communication, but it's not clear for me if you try to avoid to have a visual mutual visibility, or you try to avoid it, as it was saying in the document, I think. So could you elaborate, explain me what is the idea or the originality about that, this question of mutual?
The point is that mutual visibility would constrain too much the interagent relations. And we actually do not need mutual visibility because we consider that communication allows for retrieving the relative position measurement. So yeah, maybe it was not really clear on the document, but it's the objective is neither to prefer mutual visibility or a one-way visibility, is to not consider it, and that's why the weight is designed in this way, where if either one of the two visibility function is 1, then the full symmetric weight is also at the maximum value of 1. So we do not enforce or prefer any of the configuration between mutual or one-way visibility.
Okay. So, but I think I need to return to your document to have a better understanding of what is possible and how to use this approach. It's okay. I understand the main principle. Thank you. I would like now to go to the second part of your work about the control with the user and the haptic system to control. So you mentioned that you have a distributed or decentralized system at the beginning. You speak about decentralized systems, but at a point you propose the centroid control approach.
Yes.
And I was thinking it's if the centroid control require full connectivity or not, and if maybe this centered control implies necessary a centralized system or not.
So in any case, there is a central ground station that is not, each agent implements the connectivity maintenance algorithm on its own way and communicates with the ground station. It's true that for the first and second control methods, communication, I mean, for any control method, communication is required only with the controlled agents because the others are autonomous. However, indeed, in the centroid approach, we control every agent at the same time. And also, which makes your question really interesting, is in this slide, we see that the Q matrix is actually a combination of all the QJ matrix. And so this has to be centrally evaluated. I didn't find in the literature a way to compute the pseudo inverse in a decentralized way, and so so indeed this computation has to be central.
Yeah, I think it's an open question. Yeah, at this point today. So that's interesting that you precise that for me. Okay.
Yes.
Okay, but I think it's an interesting question, an open question to explore. Yeah.
Also, I can stress that having a globally connected graph allows for the control of one agent, even if it's not directly practically connected to the remote ground station, through what I mentioned, I think in the thesis, an ad hoc network, which is basically just networking among the agents. So if there is a few agents that have, as I said before, if there is a few agents that can communicate remotely with the remote operator through communication in between the other agents, the control input from the user could be kind of forwarded, routed, sent to the controlled agents.
Okay, sure. Thank you for
more delays, of course, but
yeah, with the problem of delays and communication.
Yes.
And so it will be very interesting to have real experiments of such system, such complex system. But I think it's a huge challenge to design and real experiments of such system.
Actually, you might know, but simulating communication with ROS2 is really complicated, and it was actually a topic we discussed a lot with colleagues that worked on the same software architecture. So how to simulate communication with only local neighboring agents. One approach would be to have open topics for each agent, and the agent will communicate only on these open topics. The other way was to have a central node that simulates a communication system, just as the sensing system, which I recall I have a central node that knows the position of every agent and their field of view and sends the corresponding value. So actually, that's this second approach I used. So every agent sends the communication data to a central node that distributes it to the connected agents. This approach is not scalable because it's central, but for simulating with ROS2, without having real radios on the drones, I didn't find any better way. I mean, we could use other tools alongside ROS2, but I did not explore this way because it was not my point.
Yes, on this specific question of simulating the communication in a realistic way. I have actually a PhD student that's finishing his PhD. That's probably which is Théotime Balaguer. Yes. That's defined the dancers co-simulator. That's allowed to connect any physical simulator with any network simulator, and in particular NS3. The NS3 reference network simulator. Yes. And so it is able to have very realistic simulation, and especially for drones. So maybe you can have a look on that.
I'm aware of his work.
Okay, so it's maybe a way to try to go deeper in the question of a realistic simulation with communication.
Combining everything would be really nice.
Okay. Now maybe a question about the haptic evaluation. So it's not my domain of expertise. So I have probably a very naive question. You mentioned you measure the effectiveness and intuitiveness, and so I was thinking, what is exactly the difference, and how we can measure these two things? Could you elaborate a bit to explain me?
So this was actually for the user study. The way we do it is we first have a questionnaire asking how every user is experienced with different haptic feedback control systems or virtual 3D environments. This is to evaluate how diverse is the range of user in the user study. And after each flight, I would show another poll where I ask the users how efficient they felt in achieving the task. So they were ranking their felt efficiency from 0 to 5. So the efficiency was did they achieve the task effectively? So most of the time it was in terms of execution time, but for the coverage it was in terms of coverage. And the second one is intuitiveness. So this question was a bit different. It was considering, because in the case with no haptic feedback, they, for instance, for the single leader control mode, they will try to go forward and the agent will slow down because it would wait for the neighbors because of the connectivity maintenance force. And so this was to highlight whether or not they could, they would understand. So of course, people that are aware of the connectivity maintenance algorithm would still feel it a bit intuitive only with visual feedback, but most of the other operators would benefit from this force feedback that will inform them that the drone has to wait for the other agents behind. So that was the two questions. And the last plot is from the actual measured value, so it was not on the question.
Yeah. Okay. Thank you. That's clarifying for me the meaning and the way you measure that. Maybe about the score. So can we conclude that with these values, it is good, it is average? What do you think? What can you say about
so here it highlights that indeed, and especially for single agent control, where it's even more intuitive, because the force is the force applied to the agent directly. We can see that with haptic feedback, it's better in terms of performance, intuition, and felt experience effectiveness. And the actual completion time, the better result is explained by the fact that the user could feel the force, but could choose to counteract it. So, of course, not breaking connectivity. So they were tasked and informed that if they resist too much, they might break connectivity. And actually, it happens mostly on the Centroid case, where some users broke connectivity. And so I redid the experiments. So they had more freedom on the control over the drone because the drone was not automatically following connectivity, but instead the user was adapting to the force feedback.
Yeah, on the intuitiveness curve with haptics, we have seems to have a valley, and so this may be meaning that there is two groups of persons.
No, it's just that maybe the scale of the plot is not well done, but they could grade only using integer values, so from 0 to 5. So it's just that some people replied 3 and other 4, and so no one could reply 3.5. So that's why there is this value.
It's more linked to that. Okay, thank you. I would just to finish by a general remark. That I think that you made a lot of work with many experiments, simulation, with development, and also with connecting to an haptic system for the last part of your PhD. This is very interesting. About the development, software development. So you will diffuse the work. You mentioned that it will be done. It's not yet done. In which way you can diffuse or valorize that?
So
something?
we were a few people working on this, and at some point our interests diverged. So I think I want to do a release of my version of the work. I have to. I think administratively, I have to identify what are my limitations in terms of license and property. And the work also needs some more documentation, even though I tried to do it in a clean way so that it's understandable for.
Okay, because I think that it's interesting for the community to have access.
I think so too. I try to make it accessible.
Okay, so that's finished for me. Thank you for your answers, and once again, congratulations for the nice presentation. I appreciate a lot.
Thank you.
Thanks.
Thank you. So it's now time for me to ask questions. So I will remove my my president role and just ask questions in a member of the jury. So first of all, I would like, as mentioned by the previous member, I would like to congratulate you for your work and for your very nice presentation. It was very complimentary to your manuscript, and you had like very nice videos, and it illustrates very well like what you did and to better understand your contributions.
Thank you.
And as mentioned also before, you did like I think like a work at the convergence between different fields like robotics, multi-agent systems, but also haptics and drone specificities, and you have like to put everything all together to find your way and find the contribution that you could do in that field, like given all what has already been done in each of these very wide field. And I think you did a great job of like finding contributions and being able to propose something quite interesting with a lot of opening questions, as we did mention, but also like it means that there is still a lot of things to do in that direction, which is also a good sign for you. And because we already discussed about like what you did during like all your PhD, I know that, and I would like to underline this here, I know that you did a lot of like software development during your work. And as Olivier asked, I think you might be able also to somehow disseminate what you did in terms of software development, because I think you did like a huge amount of work on that side. And it's not visible when you see the contribution, but it's like a lot of work. So I would like to underline this in what you have done in your work. So I have like some questions. So a lot of questions have already been asked, but I still have some questions. First one is about, so of course I am a little bit like, yes, because I am a haptics person. So I will have first question about haptics, and I would like to ask a question about the design of the haptic. So Francesco already start to ask question, and for me, what could have been of interest, of course, is like, because you have a haptic system, then in a haptic system, you have like a lot of variants in terms of haptics that you could provide. So as you said, you could have like tactile or whatever, like other type of haptic cues, but even already like with 6 degrees of freedom haptic system that you have a lot of different opportunities, like being able to know and to be aware of the number of drones, for instance, that you are manipulating. And I would like to have like some feedback from you about how you could envisage like improving the diversity of haptic intensity or diversity only with your haptic system that you use, and how you would like to change or to improve your system.
So that's a nice question. The haptic interface as of now is really only focusing on the connectivity maintenance task, which is actually in most of the scenario the secondary task of the. It's really, as I said many times in the work, an underlying assumption of many decentralized systems. And as you saw in the scenarios the user had, it was the main task was to reach objectives or discover areas. But for this work, we felt that providing haptic feedback on this specific scenario would require knowledge of the environment. And so why not having a fully autonomous system, for instance, for reaching objectives, if we already know the objective location, the robotic team knows the objective location. So providing haptic feedback, force feedback, guiding the user towards the location, for instance, was, in my sense, not the objective of this work, because it would require knowledge of the objective location, and then having the task automatically achieved would be feasible. So in terms of decentralized and multi-agent requirements, providing additional force feedback, I think I don't see interesting ways in this particular domain to do it, because I struggle to find what kind of feedback force feedback could be achieved by the user. I mean, it could be interesting maybe to provide feedback when a new agent is sensed or an agent is not sensed anymore. We could think of maybe a small vibration of the handle, a small click. But I think the system as it is now is sufficient to provide most of the information needed by the user in terms of connectivity instruments.
Okay. And did you try also to decorrelate all the degree of freedom that you can have?
Yes. Not all. I tried to, let's say for the single agent control, you only provide 4 degrees of freedom to the agent because it's a quad rotor. It's not fully actuated. You don't control its orientation. So in this case, the orientation of the handle was locked. Only the yaw could be controlled and the translations. I tried to decouple these motions, so it was locked here, but also there is the dead zone force, that helps the user to remain in the center, which helps the user to only control the orientation of the agent without moving the handle, because without this kind of force, it's really hard for the user to remain stationary and only control the yaw. So that's why there is this joystick-like force helping to remain in the center. For the centroid control, I also lock the handle in the user study specifically, where the user don't have control over the panning and tilting. So the orientation of the handle this way is deactivated, but they will control the scaling using this motion, and so this one was allowed. So that was some kind of decoupling of the control inputs as well.
Okay. Yeah. Great.
Okay.
So still in the interface, but something that you did not explore in your work, is like the way we could interact in 3D, like with your system, because
Yes.
for the moment, I mean, so you did like very nice scenarios, like in simulation with Unity, and then of course we would like to be immersed in 3D with this scenario, especially because you have like 3D, you are managing 3D information and you are handling them, so you already mentioned with Francesco that of course a nice opportunity could be, for instance, to go into the immersive room and being able, even in a simulation, to be able to interact. But if you like to interact in 3D, then you need somehow to also translate the haptic interface that you have in the 3D scenario. And then, for instance, for selecting the drones, yeah, you did not speak about like a selection technique that you used, or how did you choose it? And because it could be quite tricky in 3D to select things, especially when you have drones working in all directions.
So actually, I did not cover it in the oral presentation, but we designed a method to automatically select a leader from the group. And actually, this selection method is based on the visibility function, because we observed that sometimes looking around could be locked by the connectivity maintenance algorithm. So we wanted to control a drone that is the most free to look around from a subset of agents. And so this function was called in the user study when pressing a button on the virtual's handle. So this it goes in opposition to what I said before, because it would require to know the objective type. So then we would select the best agent from the subset of agents with the correct sensor. But for a 3D interface, we could imagine when the user presses a button, it shows on a list the types of sensor, let's say, of the team. and the user can select which sensor they want, and then it will automatically control the agent or agents with this specific sensor using the automatic leader selection function.
And do you think like a grounded haptic interface is like the best interface in that case, like when you are like immersed in the 3D environment?
I think so. Well, the immersion in the environment will depend on the application. If it's still remote operation of the robotic team with maintaining connectivity, having the user immersed, I don't see real interest in doing so, at least in the immersion room, where the point is really to be immersed within the team. So in this case, I think having the classic force feedback device like they have in the immersion room is useful. But on the other hand, having the human user as part of the robotic team, as I showed in one of the illustrations, making it in such way that the user is in the immersion room and the agents are flying in another room. There, having like the work presented before, wearable feedback device that guides the user to maintain connectivity would be useful, and it would be safer than being in the room with the quadrotors flying. And this could be interesting both for using the immersion room, which provides immersion in the scene, and using different types of haptic device.
Okay, thank you. So still like work like still on the feedback to the user. So you have visual and haptic feedback, and this feedback are somehow complementary. Like and you did not discuss like about the weights that you could have for each of them. I mean, like because you could have like situation where haptic feedback could be very useful because you have like occlusions, so you are not able to see everything. So of course, haptic could be like a nice alternative. So how do you see the complementary like of how you could weight like both visual and haptic feedback?
Yeah, it will.
In that case, in the scenarios that you have.
In the scenarios I have, I'd say, because we assume that we are able to reconstruct the position in a global frame, visual feedback can be kind of not perfect because it's never perfect, but it can be, we could see agents through occlusions, through walls. However, haptic feedback is still really useful, and it could be even more useful in case where the agents need to go through a narrow space, and the connectivity maintenance algorithm cannot allow for this, and there is a deadlock solution situation, basically, which has been solved in the literature, and providing haptic feedback in such case, where it might be tough to identify visually, could be of interest. And weighting the two approaches, I think they are both really useful and dependent on the visibility, because when you, for the single agent control mode, you go forward, so the vision is pointed forward. You don't see where are the agents behind. On these videos, we saw the links, the colored links getting red. So this is visual information that the agents behind are a bit slow, and the leader agent needs to wait. But in the user study, the users do not see the colored links. So the haptic feedback is more interesting than visual feedback in this case, even though because it's a 3D scene, we could, with the mouse, move the camera, scroll back to zoom out, look around. Okay. So both the approaches are useful, but using this movement of the camera would require using the mouse because of the way it was done. So it's not so useful.
And do you think, like, for instance, like if we are like in a learning approach, for instance, for learning to control everything, that's something we could balance somehow, like for...
Yes, of course, yes. Showing for instance, showing the links between the agent could help the user identify that when the links are red, it's because, and I feel the force, so that means the connectivity weakens. So to learn what the actual force feedback means, it could indeed be really useful to see that. And also to show the blue arrows that I show on some video that shows the contribution of the connectivity force. that also could really help the user understand what's happening and why does they feel this kind of haptic feedback in case where it's less intuitive, such as a pin control or centroid control.
Okay. And then my last question is maybe like an open question. I don't know. Like when you speak about like your first algorithm about connectivity, so you have like this visibility term, which refers somehow to the sensing. And when you speak about sensing, it's mostly about camera sensing.
Yes.
And we know that we can do like tactile sensing, like being able so to feel. Like especially when you embed this in the drones and you're able to feel also the environment. So it means that maybe not like when you have two drones, because when you feel them, it means that they are too close each other, but you can feel the environment, and this is something that could be of interest also, in addition to having the connectivity between the drones.
That's
And
nice.
what about like in the visibility term, like having this tactile something? Is this something that could be feasible for you? Or?
Having tactile sensing in the visibility term, I'm not sure I understand.
Yeah, because like for the moment you have only camera information.
Yes.
So you have
okay. But these weights are designed to constrain and ensure interagent interactions.
Yeah.
So as you said, having tactile sensing in between agents is maybe not so useful or interesting. I'm not sure.
When the camera is not working, for instance, if
Yeah,
you have
yeah,
in a dark environment.
Yes.
I'm just asking if it's feasible. I know it's complex, but
adding new weights is of course feasible. It's the way the algorithm works is by multiplying all the weights together so that it remains bounded between 0 and 1, and having as long as the new weight would follow the design requirements, so the vanishing gradient and vanishing values for the weight, it's feasible to add new weights. The only thing is that we observed that sometimes where the weights are not, let's say there is a multiplication of multiple weights that are in between 0 and 1, then the total weight will be lower and lower, like 0.5 times 0.5 is 0.25. And so sometimes the algorithm will struggle to increase the gradient when multiple weights are below 1. And so in this design, I mean, experimentally, I found that having multiple weights that are not adding more weights basically makes the algorithm a bit more unreliable. But it's still possible to add new weights depending on what interaction we want to model and ensure between two agents.
okay, thank you. So thank you for the answer to my questions. So and congratulations again on your. So now it's time for the supervising team to speak. We'll start with Marco.
Okay. First of all, thank you, President. Thank you, the advisors, for inviting me here. Thank you for your presentation. I think the delta between the last time I saw your work and now, it's really impressive.
Thank you.
So I had a bunch of industry-related questions, but my former colleague Francesco and Fabio already addressed them very well. So I will try to go back to very quickly to the theory. If you can go to your limitation,
Yes.
limitation slide, you spoke about a weight that is missing.
Yes.
So no line of sight occlusion awareness capabilities.
Yes.
So that's a weight that is missing. So the idea is that if you are looking at a drone and you have another drone that will go like in front of it, you cannot avoid that.
Not in this work, but in the literature it has been addressed. Yes. So I know you. I mean, I think your question was leading towards this. Some work in the literature are using connectivity maintenance with line of sight occlusion capabilities. Also obstacle avoidance capabilities, but this, as I said, is not possible because of the limited field of view of the cameras. However, the line of sight occlusion is already achieved in the literature, and I think it would require minimum additional work to implement it in this work.
Okay. So you didn't study it because not because it's hard to do, but because it just had the complexity to the algorithm.
Yes.
Less stable.
And it was not a contribution because it was already so addressed.
One last very big question. You saw my work with a heterogeneous team. So if you were to, you have a homogeneous team. If you were to consider, like for your DARPA Subterranean challenge, if you were to consider an heterogeneous team, well, how would you do that? So since you have cameras.
So the way we design the weight is not like each weight can be different, can be parameterized in a different way for each agent. So I tried multiple experiments. One where there was only there was a blind agent. One where there was even a grounded agent. So the algorithm could not control its altitude. And I found that it is not a problem for the connectivity and maintenance algorithm to adapt to such constraints. However, having too much constraints, like of course, if the team has a grounded agent, the flying agents cannot go too high in order to maintain the other agents in their field of view. But having heterogeneous teams in this application consists just of adapting the hardware to a high-level controller interface in order to account for the limitation of each agent and to parameterize the high-level controller in order to identify these limitations and account for them. Thank you for the questions.
Okay, so now.
Yeah, thank you very much. So thanks very much for having come here for the defense. And I don't have particular questions. I just want to congratulate Maxime because, as everyone said, the work has been really a lot, and a lot of the work is not visible from the presentation because there have been a lot of software development over the years, which Maxime didn't have time to present. So you cannot really appreciate it, but I saw it first person, so I can. And also, let's say, putting everything together, doing the experiments that you've seen in the video has been a lot of work, setting everything up, tuning everything, finding the participant, doing the experiments analysis. So, of course, everyone would be happy, and Maxime the first to do real experiments with robots, but honestly, for a PhD thesis that lasts 3 years, it's the engineering effort of having really drones with cameras on board and everything. It's too much, I think, for a PhD thesis, which is only 3 years. Because... So yeah, I don't have anything else to add, and congratulations again.
Thank you.
Yes. So first of all, I would like to thank the jury, the president, the rapporteur for their work, for being here, and thank you, Maxime, of course, for your presentation. We have seen a very good progression from the first versions to today. So it's very nice, very clear, and I think also all the supports, the video, you really did a good job in showing your work. And I think we also had fun to design all these Unity environments, adding all these the gas leaks, all the different scenes. I think it was something also quite new for you, right? So you also explored for the very first time this new technology, which was not easy, but it's the result is very, very nice. So you should be proud, I think, of the work you have done, and hopefully the last paper will be published soon, so that we have also a proof of all the quality of the work. And as also Paolo said, you did also a lot of technical work around this, with this Olive framework, collaborating with many other students to build all this framework also for others, people to be able to use it, which is definitely valuable and an asset for the team from today onwards. I don't have particular questions. Maybe I have one question. So what was the hardest part, the hardest thing you had to do throughout the PhD?
Well, as an engineer, I would say most of the math theory was quite hard for me. It was really interesting to learn and relearn some things because I still had, of course, some classes and courses about all those stability analysis. But using it as a tool, adapting it to my scenarios, like we see some work with matrices for the centroid control, and I always like to relate on how mathematics are acting physically on the robots. And the more you go high and deep into math, the less it's easy to understand what's the actual action of what you do.
The math magic.
Yeah. So this was the hardest thing for me, I think. But it was still super interesting. And as you mentioned, I learned many things from many different fields, developing in Unity, using haptic feedback, flying multi-robot systems, even though I don't really actually fly. All this stuff is a really great package for, I think, my future in research. So
Great. So thank you again.
Okay, so thank you. So it's now time for us to deliberate. So,
Yeah.
Olivier, do you have another link?
Yes, you can use the link, my personal page that I
Yeah.
shared.
Okay, so I leave this one and I join you on the other.
Yes, please.
Exactly.
Thank you.
and you can join this one after if you want.
Yeah.
We'll back. We'll come back. Okay.
Désolée, je fais de la traduction en temps réel, et contrôler un système de drones. Donc, le jury a été particulièrement impressionné par tes efforts importants, notamment en termes de développement logiciel, et spécialement pour développer du coup toutes ces simulations d'environnement avec des drones dans des environnements variés. Et donc, tous ces développements ont abouti à des outils qui sont sûrement utilisés par la communauté et puis qui ouvrent plein de perspectives en termes de recherche. Concernant ta présentation, donc le jury a apprécié la qualité de ta présentation, qui était très bien organisée, claire et bien présentée en anglais. Elle était très bien illustrée avec des vidéos qui étaient très complémentaires de ton manuscrit. Et le jury a également apprécié les réponses aux questions qu'ils ont pu poser, que ce soit sur des points techniques ou bien des questions plus ouvertes, ce qui montre du coup ta connaissance du domaine et puis du coup vraiment la confiance que tu peux avoir dans les différentes connaissances et les différents domaines que tu as pu aborder au cours de ta thèse. Donc pour toutes ces raisons, du coup le jury a décidé à l'unanimité de te décerner du coup le grade de docteur en automatique productique et robotique de l'université de Rennes. Félicitations.
Merci.
Avant les festivités, je crois que tu as un serment
Oui.
à faire.
Je vais lire le serment. En présence de mes pairs, parvenus à l'issue de mon doctorat en robotique, et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Du coup, c'est le moment où je peux remercier. Bon, comme tout le monde, j'ai rien préparé. Je vais remercier en français, pardon. J'aimerais remercier mes encadrants pour m'avoir proposé ce sujet, m'avoir accompagné pendant ma recherche. Les membres du jury pour leur retour intéressant et très constructif sur le travail que j'ai proposé au cours de ces 3 années. Pour votre présence ici et les questions que vous m'avez posées et votre opinion sur mon travail. Les autres membres du jury pour évidemment leur présence et leurs questions également. Et maintenant, j'aimerais remercier ma famille qui m'a accompagné pendant ces années. Ça n'a pas été toujours très facile. J'aimerais aussi remercier Olivier qui assiste à distance, qui n'a pas la chance d'être parmi nous en présence, et avec qui je vais continuer quelques projets de recherche dans les années à suivre. J'aimerais remercier mes collègues ou amis qui m'ont vu travailler des fois bien, des fois de manière plus compliquée pendant ces années, qui m'ont beaucoup soutenu. Même ceux qui ne peuvent pas être là, je pense à Nicolas, Maxime, John, Antonio. Je suis un peu le dernier de la génération. Donc merci beaucoup à eux. Je sais que même s'ils ne peuvent pas avoir ces remerciements, ils savent ce que j'en pense. Et aussi mes amis pas du labo qui sont venus aujourd'hui pour ce jour important pour moi et qui m'ont quand même accompagné au cours de ces années. Donc voilà, merci tout le monde. J'espère que j'ai oublié personne. J'ai sûrement oublié des gens, mais merci beaucoup.
Take a picture with the jurors.
Yes.
And Olivier, reste là, on fait
Je vais vous laisser aller manger ou boire la paix.
on fait la photo, attends, reste là.
Oh, d'accord. Ok.
Tu vas prendre en fait.
Ah, moi, je vais me mettre à côté de toi.
Je peux m'approcher.
I don't know if you want to take also the.
It's fine.
Okay.
Ok, merci, salut Olivier, à la prochaine.
Merci.
Salut, merci, à bientôt.
À bientôt.
Bravo, félicitations Maxime.
Merci beaucoup.
Ouais, à bientôt. Merci à tous.
Félicitations.
Merci beaucoup.
Congratulations.
Okay.
So perfect timing.
So we go to
Go to